This video is about energy changes in simple harmonic motion. To learn about these energy changes, we'll examine an oscillating spring and a simple pendulum. Let's start with the spring. Picture the spring in three different positions while it oscillates. When it's fully compressed, when it's uncompressed, and when it's fully stretched. As you can see, there is a small object attached to the spring. As the object oscillates back and forth and the spring reaches its fully compressed position, the object is at one of its maximum displacement positions. Since the spring is fully compressed, elastic potential energy is stored in the spring. At the maximum displacement position, this elastic potential energy is at its maximum. At the same time, at this position, the object stops for a moment. Therefore, its speed is zero, so its kinetic energy is also zero. Then, the spring starts to decompress, and the object starts moving to the right. During this, the elastic potential energy stored in the spring is converted into the kinetic energy of the object. At some point, the spring reaches a position where it's uncompressed. At this moment, the object is passing through the equilibrium position. Since the spring is neither compressed nor stretched, here elastic potential energy is zero. Since energy cannot be lost, only converted into a different form, we can conclude that at this point the speed of the object is maximum, therefore its kinetic energy is also maximum. After passing through the equilibrium position, the spring begins to stretch and the object starts to slow down. At some moment, the spring becomes fully stretched. This is the other maximum displacement position of the object. Since the spring is fully stretched, elastic potential energy is at its maximum. The object stops for a moment, so kinetic energy here is zero. So when an object oscillates on a spring, assuming that there is no friction, elastic potential energy is converted into kinetic energy, and then kinetic energy is converted back into elastic potential energy. These conversions repeatedly happen while the object oscillates. Let's look at energy changes for a simple pendulum. Let's displace our pendulum all the way to the left, release it and let it pass through the equilibrium position, and then allow it to swing all the way to the right. When the pendulum is all the way to the left at its maximum displacement position, it is at the highest possible point above the ground during its motion. Because of this, the gravitational potential energy of the pendulum bob is at its maximum. If you picture the motion of the pendulum, you can see that at this point it stops for a moment. This means that its speed is zero, therefore its kinetic energy is also zero. Then, as gravitational potential energy converts into kinetic energy, the pendulum bob moves to the right, loses height, and gains speed. At some point, it reaches its lowest possible height above the ground and is passing through its equilibrium position. If we assume that at this position height is zero, then we can conclude that gravitational potential energy is zero. Otherwise, we could say that gravitational potential energy is at its minimum. By now, all gravitational potential energy has converted into kinetic energy, so speed is a maximum and kinetic energy is maximum as well. After passing through the equilibrium position, the pendulum starts to gain height and lose speed. At some point, it reaches its other maximum displacement position all the way to the right. Here again, gravitational potential energy is at its maximum, and since the object stops for a moment, speed is zero and kinetic energy is zero. So in case of a simple pendulum, energy conversion happens between gravitational potential energy and kinetic energy. This wraps up our discussion about energy changes in simple harmonic motion and completes the final video of subtopic 4.1. In the first video of subtopic 4.2, we'll see an introduction to traveling waves.